Assalamu alaikum. In this lecture, we are going to talk about the different type of connections for the directional relay that can be used in different parts of the power system. In the last lecture, we talked about the 90-degree connection, and for that we have calculated the ICC as well as VPC that has to be used for the line-to-line faults. For example, in this case, we have phase A related fault, so we were considering ICC equal to IA, and the VPC, the potential coil voltage, was considered to be equal to VBC. Similar to 90-degree connection, we can have a 30-degree connection as well as a 60-degree connection. And for different phases, phase A related fault, phase B related fault, as well as for phase C related faults, we will have a combination of currents as well as different voltages, and that depends on the phasor diagram representation that we done in the last lecture, that what VPC should be used for what type of connection. But it was clear from the last lecture that we can easily determine the VPC if we know the pre-fault current and voltages. Pre-fault currents and voltages of the system. For example, we talked about the 90-degree connection in the last lecture, and we considered phase A related faults. We know the phasors are VA, VB and VC, and for the unity power factor condition, IA, IB and IC will be in phase with the respective voltages. Now, as I am saying that it is a 90-degree connection, so there should be a voltage that has to be considered as VPC at 90 degree from ICC. So this will be your VPC, and this IA is ICC. So there is an angle of 90 degree between ICC and VPC. So we just have to find this voltage VPC that has to be used for the input of the directional relay. And we know that from the phasor diagram, it can clearly be seen that VB plus minus VC is actually equal to VBC. So ICC in this case is IA and VPC in this case is VBC. So similarly, we can find the VPC values for all different type of currents and connections using this technique. Now, in this lecture, we are going to just talk about different type of connections that are being used in different part of the power system. For example, the first one that we will talk about is a 30-degree connection with MTA equal to 0 degree, and maximum torque angle is equal to 0 degree, which is denoted by tau. And we are going to draw the phasors for this particular type of connection. We have VA, VB and then we have VC. All these three voltages are at 120-degree angle from each other. And if we are talking about the unity power factor, then IA, IB and IC will be in phase with VA, VB and VC. So this will be VB and this will be VC. So this is IB and this is IC. For this lecture, I am going to call this phi as power factor angle. Theta is the angle between ICC and VPC, and tau is the maximum torque angle. Now if I am considering the 30-degree connection, so I have to first find the VPC value, which should be somewhere here, 30 degree. This is your ICC, because I'm assuming that the fault is being considered. So all the faults that are considered in this case are related to phase A in one way or another. So first I have to find VPC, that is in this direction, and from the phasor diagram I know that VA minus VC will be the VPC, which will be equal to VAC. So in this example we have ICC is equal to IA and VPC equal to VAC. So these are the two inputs to the relay. Now in order to find the torque value at unity power factor, so first I will be considering the unity power factor value, means phi is equal to 0 degree. And from the previous explanation we know that the torque value for this type of relay will be equal to K VPC ICC cos theta minus tau. This is the maximum torque angle between VPC and ICC, and phi is the power factor angle. Tau is equal to tau max cos theta minus tau. So I will be using this equation for the further explanation, because when cos theta minus tau is equal to 1, then torque will be equal to torque maximum. Now at unity power factor, tau max cos theta minus tau will be dependent on the value of theta as well as tau, right? And the angle theta in this case will be equal to 30 degree, because the angle between IA, which is ICC, and VPC is equal to 30 degree, and we already know that tau is equal to 0 degree. Now putting these two values in the equation, you will get tau is equal to tau max cos 30 degree, and this value is equal to 0.866. So this is the torque value when we have a unity power factor condition. Now if I will rotate this IA in anti-clockwise direction, means now if I will consider power factor angle of minus 30 degree, it means that now the angle between the IA and VPC should be equal to minus 30 degree. So IA will be over VPC. So now phi is equal to minus 30 degree, but in this case theta will be equal to 0 degree, because now VPC and IA are in phase. So now torque value will become cos 0 minus 0, and this value will be equal to 1. So tau is equal to tau max. So when the IA current is lagging the voltage VA by 30 degree, it will be in phase with the potential coil voltage, which is VAC, and the torque at that time will be the maximum torque that is generated in the disk of the directional relay. Now for the third case, IA is moved to the position of minus 60 degree, which means that power factor angle theta, that is equal to phi, has now become minus 60 degree. So if the power factor angle is minus 60 degree, it means that now the angle between IA and VPC is 30 degree. Now if theta is equal to 30 degree, torque will be equal to torque max cosine 30 degree minus 0. So this will be 0.866 times the maximum torque, right? Similarly, if I have to find out the value of the torque at 0 power factor angle, which is this one, when the angle between the voltage VA and IA will become equal to 90 degree, this is known as a 0 power factor angle. So if power factor angle is equal to minus 90 degree, theta will be equal to minus 60 degree, and the tau or torque will be equal to cos 60 degree, and this is equal to 0.5 times the maximum torque, which means that from this point to this point somewhere, we have sufficient amount of torque being produced in the disk. For example, at 0 degree we have the value equal to 0.866 times the maximum torque. At power factor angle of minus 30 degree, which is this one, we have the maximum torque that is being applied over the disk, and at angle minus 60 degree of the power factor angle, the torque is 0.866 times. And lastly, for the 0 power factor angle, the torque is 0.5 times the maximum torque value. So we can use this type of relay when there is a chance that the fault current will be somewhere between 0 to 70 degree. Then we will have enough torque being produced in the disk to operate properly. But if you will use somewhere closer to the 90 degree, which is the case when we have highly inductive current, so we cannot use this sort of connection in that case. So where do we use this type of directional relay connection? For example, we have a feeder and there is a load attached to this one. Normally this load current IA is lagging, and that lagging is somewhere close to 30 degree. So if there is a fault in this line, then there is a possibility that this current will further lag the actual load current. I'm only talking about the phase value, because the magnitude will be higher in the fault current case, but the load current will be smaller. So if there is a fault in the line, then the angle might be somewhere 60 to 70 degree value. So in that case, if the current is somewhere in this region and your maximum torque angle is actually this one, maximum torque angle is this one, tau is equal to 0, means IA and VPC are in phase. So if this is your maximum torque angle, then you will have zero torque line somewhere here, and if this is your zero torque line, then this is your restraint region, this is your restraint region, and this is your trip region. So whenever there is a fault in this line, there is a chance that there will be a fault current in somewhere 0 to 70 degree value. And if there is a fault with a larger magnitude with respect to the load current in this direction, then it will be in the trip region. For example, this is your IF. So if it is in the trip region, then the directional relay will easily detect this one. So all the feeders which have load at its end have a 30 degree connection of the directional relay. So this was the first example of one of the connection that are being used in the directional relay, and that is used for the normally loaded distribution line, for example. Now in the second case, we have a 90-degree connection with MTA of 45 degree. So the second case is 90-degree connection with MTA 45 degree. So this is your tau. So we will be using the same procedure that we have used for the 30-degree connection. First we have to decide what will be the VPC. This is your VA, IA, VB, IB, VC, IC. And for the 90-degree connection, there should be a voltage somewhere here, so that we have 90-degree angle between ICC, that is IA in this case, and VPC, which will be VBC in this case, minus VC, right? And maximum torque angle is 45 degree. So this is your MTA line. So if this is your MTA line, then this will be your restraint region, and this will be the trip region. The same steps that we have used for the 30-degree connection with 0-degree MTA will be used here in order to check whether this 90-degree connection will have some different result in comparison to the 30-degree connection or not. For example, first is the unity power factor condition. Unity power factor condition means phi is equal to 0. Phi is equal to 0. Then we have theta is equal to 90 degree and tau is equal to 45 degree. Means IA is in phase with VA. So the angle between VA and IA is 0 degree. The angle between IA and VPC is 90 degree, and MTA angle is constant, that is equal to 45 degree. The formula for the torque is tau max cos theta minus tau. So this is 90 degree minus 45 degree. This will be cos 45 degree, which is 0.707 times the maximum torque. So this is the torque value when we have a unity power factor condition. Now what if the power factor angle is equal to minus 30 degree? Minus 30 degree means now IA has been moved to this point, IA minus 30 degree. So phi is equal to minus 30 degree, theta is equal to 60 degree, and tau is equal to 45 degree. Maximum torque angle remains same, 45 degree. The angle between IA and VA now in this case is minus 30 degree, and the angle between IA and VPC is 60 degree. So this angle is 60 degree. Again, tau is equal to tau max cos 60 minus 45 degree. So this will give you the value of 0.967 times the maximum torque. Now for minus 60 degree value of power factor angle, theta will be equal to 30 degree and tau will be equal to 45 degree. And in this case the torque will be equal to tau max 0.967. that is same as for the power factor angle of minus 30 degree, right? Now at the power factor angle value of minus 45 degree, you will have torque value theta minus tau. Theta will be equal to 45 degree and tau is equal to 45 degree. Now in this case, this IA will be moved to this point, minus 45 degree. Now the angle between VA and IA is minus 45 degree, and the current is now over the MTA line. So if it is over the MTA line, it means the maximum torque will be produced in the directional relay. So theta is equal to 45, tau is also equal to 45. So cos 0 will be equal to 1. So the maximum torque will be produced whenever we have phi equal to minus 45 degree, or power factor angle equal to minus 45 degree. Similarly for the zero power factor angle. Now in zero power factor angle, the angle between VA and VPC is 90 degree, which represents the zero power factor, and theta in this case will be equal to 0, right? Now theta is equal to 0, but tau remains 45 degree, and the formula for the torque is cos theta minus tau. This is 0 degree and this is your 45 degree. So in this case again the value will be 0.707 times tau max. So now we are having a sufficient amount of torque being produced in the disk of the directional relay whenever we are moving IA from unity power factor position to zero power factor position. So we have at least 0.707 times the maximum torque being produced in the disk whenever we are moving this IA from unity power factor position to zero power factor position. So where do we use this type of connection? So whenever we have a line that is being ended at a transformer. So if there is a fault at this point, then the fault current will be less tilted towards the 90 degree angle in comparison to this fault. What does it mean? That there is a possibility that the angle between voltage VA and fault current will be somewhere here or somewhere here, more than 30 degree, when there is a fault at this point. For example, this is your fault F1. But when we have a highly inductive load which is represented by a transformer, so the reactance of the transformer is very high. So if we are having a fault after this transformer, then there is a chance that the fault current that will be received at this point F2 will be lagging somewhere close to 90 degree with respect to VA. The value of the current that is at F2 will be highly inductive, and it means that the current will be having an angle closer to 90 degree with respect to the voltage VA of that particular phase. So we are having sufficient amount of torque being applied to the disk whenever we are using 90 degree connection with MTA of 45 degree. So all the feeders which are ending at transformer and there is a chance of having a fault after the transformer, in those feeders we will apply 90 degree connection for that part of the power system. So these are the two different type of connections. Similarly, we have different type of connections with different MTA angles in different part of the power system, and we can assess all these connections in the similar manner before applying it to a particular region of the system. Thank you.